Welcome back, everyone. Okay, so we're going to continue on with our discussion about the quantum mechanical model and all of the new observations from Schrödinger, de Broglie, and Heisenberg. And as a result of all of that work, a certain concept called quantum numbers that can actually be used to categorize every electron in any atom exists. So here's a really good definition that you need to know. Quantum numbers. Let's take a look at what it says. Numbers that describe the quantum mechanical properties of orbitals. And so let's just remind ourselves, what is an orbital? An orbital is, and I'll do this in blue, a three-dimensional space where electrons are likely to be found. Okay, so different from orbits. Okay, don't forget that. This is a biggie. Different from orbits. Orbitals are kind of a big thing with quantum mechanics. So what these numbers do is they try and identify and locate where a specific electron is likely to be. So there are 4 quantum numbers that we're going to use to describe various types of orbitals and various electrons. Okay, so our very first one, and I'll put a 1 here, is our principal quantum number. And this is one that we're familiar with because this is pretty much can be attributed to Bohr. Okay, so we're no longer going to call the places where electrons are likely to be found orbits or shells. We're going to call them energy levels. Okay, and we'll refer to n, which is the principal quantum number, as the shell number. Well, I'm sorry, the shell number is n, but we don't use shells anymore. So I'm going to just do because shells refer to a two-dimensional space. And as we know, electrons can travel in three-dimensional space. So what the first quantum number or the principal quantum number describes for us is the size and energy of an atomic orbital. It has whole numbers because don't forget, these things are quantized. All right, so they have whole numbers. An electron cannot be between energy level 1 or energy level 2. It has to pick one. And if it doesn't have enough to get into that higher energy level, it falls down to the lower one and it'll kick off extra energy by spinning faster. Okay, it's important to note that the spaces between shell numbers is not equal. So what we're meaning is, so just like to go back in time, so there's my nucleus, my positively charged nucleus, and before we would draw our shells like this. That's wrong. The numbers between the first, second, and third energy level are not equal. In fact, the first one is like this, and then it gets farther and even farther away. So they're not equidistant, okay? I'm just going to erase this because it just illustrates a point. So as n increases, the energy required for an electron to occupy that orbital increases, which means the further away from the nucleus equals more energy for the electron. Okay, because the nucleus doesn't have that kind of hold on an electron that's farther away. And you might remember that from periodic trends. We called that effective nuclear charge. What kind of force does that electron feel from the nucleus, right? So the farther away the nucleus is from that electron, the more energy that electron is able to possess. So as we go up in energy levels, we're further and further away from the nucleus. Okay, so each successive orbital is larger because it's farther away from the nucleus. Get it? Meaning that an electron occupying that orbit spends more time farther from the nucleus. And it also means that electrons with higher energy levels are less tightly, wrote too big, bound to the nucleus, which we learnt about kind of in grade 11 with effective nuclear charge. So just to recap it one more time, the further you go from the nucleus, the higher the energy level. The higher the energy level, the more energy that electron has because it's farther from the nucleus and it's not being held, so it can go faster. Got it? All right. So, continuing on, let's take a look. Here are some principal quantum numbers. So n equals 1, n equals 2, n equals 3, n equals 4, and n equals 5. We can go up to 6 and 7 as well. Now, what Bohr saw when he did the line spectrum for hydrogen, he saw 4 lines, okay? And so that's where he got his 4 shells or 4 energy levels, right? But when they looked at more detail, they saw smaller lines in the spectrum. So they, like, not just the big lines, there were smaller lines. And that's when, this is a big one, when Michelson and Summerfield proposed this thing called a secondary quantum number. We're going to get there. But just to let you know, so the secondary quantum number describes those other little lines as sublevels or subshells. We're going to get there, I promise. So what is a subshell? I already wrote it because it's a lot. A subshell is an orbital of different shapes and energies as given by the secondary quantum number, S, P, D, and F. We'll get to that. So think about it right here. Within your energy level, you're a distance. So remember what the first energy level or the first quantum number or the principal quantum number tells us. It tells me the size of the orbital and the energy of the orbital. But then within that first number, we characterize the electrons within that even more so because those orbitals can take different three-dimensional shapes. And we're going to get to that. So subshells are still part of that primary energy level, but we're going to go into a little more detail. So if an energy level is described as a staircase, which we all know you can only take one full step, you can't go in between, one regular step actually represents a group of energy levels. Okay, so let's take a look at this picture here. Hopefully that clarifies what I just said. All right, so let's take a look here. So see how I have my first energy level. That's a low amount of energy. Okay, so let's just label this. So energy. Okay, so within energy level 1, pretty low energy. Why? Because it's close to the nucleus. And if it's close to the nucleus, that nucleus has a lot of force on it, so my electron can't really move so fast, right? So there's not a lot of kinetic energy, so hence low amounts of energy. But then let's go up to energy level 2, and you're going to see 2 lines. Okay, so see how there's 2, and we're going to get to what that means. But within the second energy level, there's 2 different places those electrons can be. And then within the third energy level, there's even more steps. So you're kind of distinguishing even within the energy levels. Okay, and you'll see how these different energy levels get further away from the nucleus. So this is close to the nucleus, far from nucleus. Okay, and since they're far from the nucleus, they can move faster, so they have more energy. So let's cut straight to the chase. Let's talk about the secondary quantum number. Okay, that explains all these different, like these 2 lines here, the subshells. Okay, so the secondary quantum number, and just for clarification purposes, it's represented by a lowercase l. Okay, so that's what it looks like there, but it's a lowercase l. So that's the variable, okay, or the symbol. This describes the shape of the orbital. Okay, so remember, we were talking about circular paths or spherical paths. So a spherical, not path, but spherical shape of an orbital is three-dimensional. There are other ones, and I kind of alluded it to one more of them in the earlier lesson of the figure 8. Well, that's what we're talking about right now. So remember, this is a mathematical model. So when we talk about the secondary quantum number, it has values from 0 to n minus 1, okay, for each value of n. And I'll explain what that means. This number describes the number or the energy of atomic orbitals. So, for instance, if n equals 1, take a look here. That's what I'm talking about right here. If I'm talking about my first energy level, the possibilities for this particular secondary quantum number can only be 0 because my rules are right here, 0 to n minus 1. Well, if n is 1, 1 minus 1 is 0. So I've got one option. If I'm in the second energy level, well, then my options here can be 0, and I'll just spell it out, 2 minus 1, which equals 1. So my options here for L can be 0 or 1. Got it? If I'm talking about a situation where n equals 3, well, my L can be 0, my L can be 1, and my L can be 2, because it goes from 0 to n minus 1, which is 3 minus 1, so 0 to 2. Got it? So what this actually means is, so let's take a look again at this diagram. Okay, I'm going to try and squeeze all these in together. So remember, L equals 1 level. For energy level 2, it could be 0 and 1, so that's 2 energy levels within 2. Within n equals 3, I've got 0, 1, and 2. Hold up. See the 3 lines? 1, 2, 3. See? Okay. So that's how we determine how many different shapes of the orbitals. So these numbers are usually replaced by letters to avoid confusion with energy levels. So it kind of makes sense. So if I'm talking about L of a value of 0, the letter used is S, and S stands for sharp. You would think it would stand for spherical, but alas, that would make too much sense, people. It's sharp. P is when I'm talking about a value of L that is 1, and P stands for principal. A value of 2 is D for diffuse. A value of 3 is F for fundamental. Okay, and a value of G, which theoretically happens, but we don't see it in our periodic table because we've run out of actual elements. Okay, so those are the situations. So for instance, if I look at my primary and secondary quantum number for n, if n equals 1 and my L equals 0, what I have here is a 1s orbital. If my n equals 2, I have a possibility of L equaling 0 and L equaling 1. So I could have 2s or 2p. And that's where those 2 lines came from. Hold up, don't get dizzy. 2s and 2p. Okay? Then, if I'm talking 3, so if my n equals 3, I have an L equals 0, L equal 1, L equal 2. My orbitals will be 3s for the 0, 3p for the 1, and 3d for the 2. And hold the phone. 3s, 3p, 3d. Whew! How's that? Hope that's good for everybody. Moving on. So, now we've got the notes, even though I already did it. That's okay. At an energy level of n equals 1, there's only an s orbital. Okay? At n equals 3, there can be s, p, and d orbitals. No stable element in its ground state has electrons and subshells higher than F. And it's because you'll see, you run out of electrons because we only have 118 elements in existence. Okay? Third quantum number. Let's do a number 3 here. Now, this is called our magnetic quantum number. So, once again, M with a subscript L. Okay? And now, this is the quantum number that describes the orientation. Because remember, we're dealing with 3 dimensions here, people. So, there's an orientation of the atomic orbital in space. Because don't forget, we're talking 3 dimensions. So the way you actually describe those numerically is between the whole number values of plus L and negative L, right? Including 0. Now, where are those L's again? Hold up. Don't get dizzy. The L is my secondary quantum number. See? Right here. Okay, so those are my L's. So for instance, if L equals 1, okay, my mathematical way to figure out the third quantum number or the magnetic quantum number is by going positive L to negative L, including 0. So I can have plus 1, 0, and minus 1. Now in this case, we know of L equaling 1, hold on, back to our little chart here. If L equals 1, I know it's the p shape. So they're all p orbitals, but they differ from each other by their orientation in space. So in this case, there's 3 orientations, right, represented by these 3 numbers. Okay, 3 possibilities. So if you think about your X, Y, Z coordinate system, mathématiques, c'est bon, okay, you're going to look at it this way. So here's my 3-dimensional orientation. How's that so far? Okay, so looking here, I was already starting with that. If we take a look, my energy level is 1. So this is my principal quantum number. Then my sublevels is my secondary quantum number. And then the possibility of different orientations is my third quantum number. Okay? So let's take a look at what that actually means. So orbitals represent electron probability distributions. Each orbital has a unique probability, shape, and orientation. Okay? So all 2s and 3s orbitals contain areas of high probability separated by areas of 0 probability. And I already said this word to you, called nodes. Remember what a node is. It's the point in the wave where there's no movement, right? And so for our purposes, if there's no movement, there's no possibility of finding an electron in that space. So my s orbitals are spherical, okay? My p orbitals are not spherical, but they've got 2 lobes separated by a lobe at the nucleus. I'm going to call it a figure 8 because that's what it looks like to me. So let's take a look at these pictures, okay? So let's take a look at these ones first. Here are our s orbitals. Now imagine them to be spheres. So when we're talking about the 1s, it's my n equals 1, right? And it's a spherical shape. So there is your concentration of electrons. But when we go to 2s, there are 2 spherical shapes separated by like a node where at that point, that white area there, no electrons will be. So no electrons at the node. If I go to 3s, remember what what those numbers mean, 1, 2, and 3. The primary number gives us the energy level and size of the orbital. So take a look. 1s, it's smaller. 2s, it's bigger. And that second kind of spherical thing is further away from the nucleus. So though electrons found there will have higher energy, right? And 3s, it's even bigger and further away from the nucleus. So they have more energy. Make sense? I hope so. Moving on to the p orbitals, my figure 8s, same thing. You're going to see a figure 8. Now this is px. See, so it's on the x coordinate axis. Py, on the y coordinate axis, and pz like this. Now, where the node is right where the figure 8 meets. So like, this right here is my node. Oops, node. Okay, it looks like 1/2 of a chromosome too. Let's not bring biology into this. Okay, then you've got the shapes for the D subshell. I'll never make you draw them. It's hard enough to draw a figure 8. But yes, that's the next one. So this would be for D. There's 5 orientations. Okay, which kind of makes sense. Because this is n equals 1 is S. N equals 2 can be S and P. And P is represented by -1, 0, 1. D is represented by -2, -1, 0, 1, and 2. So see how there's 5 orientations? That's how that happens. Okay? Because my L is equal to 2. My L is equal to 1. My L is equal to 0. Okay? So these orientations can exist in any of the 3 dimensions and are labeled using that X, Y, Z coordinate system. So let's take a look. And I've already been drawing these, but I want to remind you. Figure 6 shows us, okay, so how the 2px orbital is defined. So the number is my n value, and my n value is my primary quantum number, so my principal quantum number, right? Then my shape, or my p, is the subshell, okay? And that is my secondary quantum number. And lastly, I don't know if I can get to, I'll just circle the X. That X is my tertiary quantum number, so the M of L. And that means your orientation in space, 3-dimensional space. Okay? So if we take a look here, the d orbitals don't happen until n equals 3. Because remember, if n equals 3, L can be, and remember, L equals n minus 1. Okay, so L can be 0, 1, and 2, because it goes up to 0 to L n minus 1. And then my M of L equals -2, -1, 0, 1, and 2, because it goes from negative L to positive L, right? Including 0. So these are my options, and that's why there's 5 d orbitals. How's that? We'll have practice. Guess what? We just made it to the 4th quantum number. And this last quantum number has already also been alluded to because it reflects that electrons spin. They spin because they've got kinetic energy. They spin because sometimes they have to release energy. And so spectral data shows that an atom has a magnetic property. And this magnetic property is called a magnetic moment when you place it in a field that has magnetism applied to it. This magnetic field has 2 orientations. And what that means is those 2 orientations can be clockwise or counterclockwise. So when we talk about clockwise, we call this plus 1/2. And if it's counterclockwise, it's minus 1/2. Okay, so I'll just write that here, plus 1/2 and minus 1/2. And that means my electron can spin one of two ways. And that's how you can separate two electrons that live in the same space. Okay, so that is my final quantum number. Now we have a very important principle here, the Pauli exclusion principle. And he proposed in a given atom, no two electrons can have the same set of 4 quantum numbers. So all 4 quantum numbers can identify every individual electron in an atom. Okay, so since electrons in the same orbital have the same principal quantum number, so energy level, the same shape, and the same orientation, then they must have different spin quantum numbers, right? So different M of S's. Okay, this is important when we apply the quantum mechanical model to account for how my elements and how my electrons are arranged in the periodic table. So let's give ourselves a question to see if we understand what the heck actually happens here. So I'm going to tell you that I'm thinking of electrons that exist in the 5th energy level. Okay, so remember, L equals 0 to n minus 1. So my possibilities for L are going to be L equals 0, L equals 1, L equals 2, L equals 3, and L equals 4. Okay? So my type of orbital in this situation if L equals 0, we're talking about S. If L equals 1, we're talking about P. If L equals 2, we're talking about D. If L equals 3, we're talking about F. And if L equals 4, we're talking about G. Next, my M of L gives me values of negative L to positive L, right? So in this case, my M of L is going to be 0 because L is 0. But when I talk about P, I got negative 1, 0, and 1. When I'm talking about D, I'm talking about negative 2, negative 1, 0, 1, 2. All right? When I'm talking about F, negative 3, negative 2, negative 1, 0, 1, 2, and 3. And negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. What the heck does this pyramid mean? That means when we're talking about this particular region, this is 5s. It has one orientation. Because a sphere, because S is a sphere, there's only one orientation for a sphere. Now, when I'm talking about 5p, that's 3 orientations because P is Px, Py, Pz. Okay? And then when we talk about 5d, there's 5 orientations, right? When I'm talking about 5f, within 5f, there's 1, 2, 3, 4, 5, 6, 7. 7 orientations. And 5g would be 9 orientations. How's that? So our types of orbitals are 5s, 5p, 5d, 5f, and 5g. Oh, look at this. Give her a try. There's also within your booklet, there's a worksheet that I will post the answers to after we take it up in class. Okay, so there's a worksheet right at the end. It's like a grid pattern. Let me see if I can find it here. Yeah, it's a grid pattern called Energy Levels Summary. Okay, we'll take that up in class. Take care, guys.